Hi everybody, welcome to the lesson. This is our last lesson of the semester, in which we take a few highlights from chapters 14 and 15, which is on linear regression. We are only going to scratch the surface of things that we could talk about with regression. In fact, there are entire courses on regression. So I want you to know that there's more to it. And in fact, if you want to know more about it, you can take the advanced statistics class we offer, which will be offered. It's offered every spring. So if you're interested, that's where you can get more information. So to start with, we're interested in using an independent variable, in other words, a predictor variable, to explain or to predict a dependent variable. Okay. Our independent variable is called x, and our dependent variable is called y. That's always been the case anytime we're looking at equations. A lot of times we'll use x for the independent and y for the dependent. And later on in this section, there can be more than one predictor variable, so that's why I put variables here. But we're going to start with just one. So the simple linear regression equation looks like y equals b naught plus b1x. Okay, you could call that a plus bx. You could call that y equals mx plus b, but we call it b naught plus b1x because here in a minute we're going to be adding variables to it, and this is better notation when we add more variables. But anyway, this is the equation of a line, your basic y equals mx plus b. And we've got a data set that we're going to work with today. And here it is. We've got several variables that we might want to use to predict college GPA. So we've got the person's ACT percentile. So that's not their actual score on the ACT, that's their percentile. So a person that got 76 here did better than 76% of other people who took the ACT. Then there's their high school GPA on a 4.0 scale, the number of honors classes they took, the number of extracurricular activities they had, and then their college GPA. This is the kind of model that might be useful in deciding which variables admissions officers should consider. And so if some of these variables make a big difference, then they should be factors in consideration, whereas if other ones don't, then they might not even consider them at all. So if we look at a plot here, and you don't have to do this plot, I had to do this over in desktop Excel to get it to look right. To try to do it in OneDrive Excel or web-based Excel, that's just not as user-friendly when it comes to creating graphs. So, but I wanted to put this on here to show you what this looks like. So here's our scatter plot looking at ACT percentile on the horizontal axis and college GPA on the y-axis. So it looks like, if you remember from our correlation graphs, there's not going to be a strong relationship there. So ACT percentile is not going to probably be the best variable to look at. Okay, we are going to look at it anyway, just to, as an example, but it's not going to be our best predictor. And you can tell that because the lines are not closely along that curve or along that line. The points are not all that closely along the line. If we were to compare that, just for the sake of comparison, using high school GPA to predict college GPA, you can see that trend a lot more clearly there. But we are going to proceed with this example. And again, you do not have to do this graph. So let's talk about how to do this in Excel. And this is in OneDrive Excel. we're going to go to Stat Plus, and then Regression, and Multiple Linear Regression. Our data is in Sheet 1. We've got our variable names in the first row. We're going to click this button here to get our dependent variable. Our dependent variable, because it's the one we're trying to predict, is our college GPA. So we're going to click Add. And then our independent variable, we're going to use ACT percentile. So we click Add, and we're going to press Run. I love some of these quotes on here. This is true. All models are wrong, but some are useful. We're creating a mathematical model here, meaning an equation used to describe something. None of them are going to be perfect, but there might be some that are good. So anyway, here's our output, and it gives you a whole lot more information than you need. Here is a scatter plot, but it's got a lot of extra information on here, and that's why I didn't choose it for us to look at. I figured that might be confusing. All right, so with all this information here, there's only a couple things we're going to use. For right now, we are focused in on just the regression equation. And it just tells you right down here at the bottom that college GPA, I'm trying to highlight this, oh, there we go. College GPA is 3.0498, so that's our Y-intercept, plus 0.0038 times ACT percentile. So college GPA is our Y. And 3.0498 is B naught. Plus, and then 0.0038 is our B1. And then ACT percentile is X. Okay, so that's our regression equation. Now, I want to talk to you about how to interpret these coefficients. You may have done some of this in your Math 111 class. I know I hit this topic pretty hard in that class, so maybe if you had somebody else, your professor did too. The Y-intercept is always what Y is when X equals 0. So if you want to interpret the Y-intercept, Y here represents the college GPA when X, and X is our ACT percentile, is 0. So the Y-intercept would be our predicted GPA if the ACT percentile is 0. And there's really no such thing as the 0th percentile, but if there were, this would be our predicted college GPA. And if you think about it, 3.0498 is a pretty high GPA for the lowest possible ACT score. So that's another indication that this is not a great predictor. But again, the interpretation is that the Y-intercept, whatever that Y-intercept is, 3.0498 in this case, because that's the variable that's by itself without an X term with it, is the predicted value of Y where x is 0. Now for the slope, and in this case the slope is 0.0038, that's the predicted change in y every time x increases by 1. Okay, that's just what it means to be the slope. So in this case, our slope is 0.0038, which would be the predicted increase in GPA every time the ACT percentile increases by 1. So every increase of 1 point in ACT percentile score would predict an increase of 0.0038 in the GPA. Okay. Now, if we wanted to use this model, this equation, to predict the GPA of a person whose ACT score was in the 80th percentile, that's easy to do. All we have to do is plug that into the equation. So we've got this equation here, up here, and all we have to do is plug 80 in here if we want to predict for the 80th percentile. So 3.0498 plus 0.0038 times 80. And you can do that in Excel easily. So 3.0498 plus 0.0038 times 80. And that gives us our predicted GPA of 3.3598. Okay. Or 3.3538, I'm sorry. Now, since we're talking about making predictions, I have to give you the standard warning about predictions, which is you should not extrapolate outside the range of your data. Meaning, don't make predictions for values of x that you don't have. In our data, we only have, well, if we look at it over here, our smallest ACT percentile is 58, and our highest is, I see, a 92. So you wouldn't make predictions. It wouldn't be valid to make predictions below that or above that. So if you want to make predictions for somebody who's had the 60th percentile, the 80th percentile, those are fine. But if 58 is the lowest data point you have, you wouldn't want to make predictions for somebody in the 40th percentile because we don't have data on that. All we've looked at is whether there's a linear relationship between these two variables. And between those 2 points. If there's a linear relationship between those 2 points, that's all we know. The trend may not continue outside of those two, of the range of that data that we have. And a lot of times I'll see or hear people say, if this trend continues, then, and they follow it with some conclusion. But just about any time you see that, that's a misuse of statistics. So be very careful with that. Trends often don't continue the way they're going. Especially if you're looking at something that's happening over time, things tend to self-correct. If we're looking at, literacy rates in the U.S. population, if those are on the decline, we'll do something about it and get that turned around. So you wouldn't want to make those predictions. And the farther you get outside the range of your data, the worse the predictions are likely to be. All right, so that's it for simple linear regression. And simple linear regression is just what we call it when there's only one variable. Now we're going to look at multiple linear regression. And with multiple linear regression, you're just adding independent variables to the model. So instead of b0 plus b1x, we've got b0 plus b1x1. And I'm going to make that subscript. Plus b2x2 plus b3x3. And you can keep going for as many variables as you have in your data set, as many predictor variables as you want to put in there. So we've got variables x1, x2, and x3. And then the coefficients on those are b1, b2, b3. And then b0 is still our constant, or our intercept. So let's suppose we want to use the same data set and predict college GPA using all of these other variables. Okay, and you'll notice I didn't do a plot of this data. That's because, you know, if you've got a plot with one X and one Y, that's in 2 dimensions. We could add a third one if we wanted it to be a 3-dimensional plot. But by the time you do four independent variables, you can't do a plot. There's no such thing as a plot in 5 dimensions. So to look at this model, we're going to do the same thing we did before. We're just going to add the extra variables to it. So in StatPlus again, and again, we have to be using the OneDrive version of Excel. So StatPlus, regression, multiple linear regression, and our data is in sheet 1. We do have variable names in our first row. Our dependent is still college GPA. And our independent, and we can check all of these other variables and put them in the model at one time. All right, so you click Add to put all those in there and run. And here's all of our output. I've already copied this and put it over here. The important part, just like it was before, is this equation. So this equation here is our regression equation. College GPA equals 2.4995. So this is our Y equals 2.4995 is our B0. And we call this plus even though this coefficient is negative. So this is just the same as plus a negative 0.0218. But it's still B1 times, and this is x1, plus, this is our b2 times x2, and this is plus b3 times x3, and here we have 4 variables, so this is going to be plus b4 times x4. So this is our equation, and let's interpret some of these slopes. So if we wanted to interpret the constant, and this is less important than interpreting the slopes, but if we wanted to interpret the constant, that would be the predicted GPA if all of these independent variables were 0. So if we look at the interpretation on the first one, all of these still have the same interpretation that the slope is the change in Y, it's the predicted change in Y every time there's an increase of 1 in the X variable. So for this first one, our slope is negative 0.0218, which means that GPA would be predicted to decrease by 0.0218, on that 4-point scale, for every 1-point increase in ACT percentile. Okay, which is actually kind of the opposite of what we would expect. We would expect that increases in ACT percentile would cause increases in college GPA. So sometimes the models don't turn out the way we think they should, and that's just a fact of working with data. This is really probably because this wasn't a good predictor in the first place. For our high school GPA, this tells us that every time high school GPA increases by 1 point, we would expect college GPA to increase by 0.9235 points. So this tells us there's almost a 1-to-1 relationship here where high school GPA predicts college GPA. So that's a very good predictor. Our next variable is honors. So every time somebody takes an additional honors course, we would expect that the college GPA decreases by 0.0094. Again, that's counterintuitive, but sometimes that's the way the data turns out. And then we would expect that for each extracurricular activity somebody takes on, their college GPA would decrease by 0.1342. Okay? So the next thing we need to talk about is something called the coefficient of determination, which is called the R-square. This is an overall measure of how good the model is at predicting the dependent variable. Okay, I'm going to put that in here. An overall measure of how good the model, or how well the model predicts the dependent variable. If you have just one variable in the model, if you notice that correlation is R, the correlation squared is the same as the coefficient of determination. That doesn't work with multiple regression. So if there are some really rough guidelines here, that 0.01 is considered small, 0.09 is considered moderate, and 0.25 is considered large. So if you have something, if you have a model where you've got an R-squared of 0.25, that's generally considered to be a pretty good model. And if you want to find the R-squared, that's on the output right here. And up here, it's right here. So for our simple linear regression, our R-squared was 0.0045, which is very, very small. But once we add these other variables into it, it increases to 0.6883. So if you're comparing to these values, adding those extra variables makes a huge difference. Now let me explain statistically what the coefficient of determination is. It tells you the amount of variance in Y that can be explained by the model. And what that means is there's something that makes those values of Y different. Okay, not everybody has the same college GPA. So that's the variability. The R squared says, how much of what makes people different have we explained here? And so if we look at the first model we had, we've only explained less than 1% of what makes people different in their college GPAs. So that's not good. In the model where we've got all 4 of them, we've been able to explain almost 70% of what makes people different. Okay, so that's a very strong coefficient of determination, which tells us that we've got a good model for predicting the college GPA. If I ask you for a sentence of interpretation on the coefficient of determination, this right here is it. The model accounts for whatever the percentage is of the variation in the dependent variable. Okay? And again, what that means is that we've been able to predict 0.45%, so less than 1%, of what makes people different. Okay? Why those differences exist. Okay? Whereas down here, we've been able to predict, we've been able to explain 68.83% of what makes people different. Okay? It's easy to write that wrong. To write that incorrectly. You don't want to say 68.83% of college GPAs are predicted by this model. That's not correct. So there's a lot of variations here that would not be correct. So I would just write this down, but change this number here and change this variable here. Okay. And this is one of those things that we hope you understand, but I know that sometimes this takes a little bit of time to kind of wrap your mind around. So, if the best you can do is just memorize this or copy it, that's okay. I won't actually know the difference. That's one of those secrets your professors don't want you to know, but I'm letting you in on that one. All right, so that's it. We have hit all the highlights we have time for chapters 14 and 15. As always, if you have any questions, you can find me. See you later.